There is something that I've shared both with an expert on statistics and an expert on fuzzy logic, hoping to learn more about the subject. Unfortunately, the representative of each group, when I shared it, they insisted that it was in the domain of the other group. The expert on statistics insisted that it was fuzzy logic that I was talking about, and the expert on fuzzy logic insisted that that was statistics. So until I find what domain this area belongs to, I am simply going to refer to it as statistical logic. To find out if anyone is looking into this area, though, the only thing I can think of doing is to put together a presentation of what I currently have figured out about this, so that people who see it can tell me if they recognize it from anywhere. And if you recognize it, please comment below. Just one thing, if you are an expert on statistics, do not tell me that this is fuzzy logic, and if you are an expert on fuzzy logic, do not tell me that this is statistics. Hello, Internet. This is Sophia the Red Angel, and in this multi-part presentation, I will endeavor to explain what this statistical logic that I am talking about is, as well as what I have figured out about it. However, first I must discuss something else that it relies upon, and that is a specific kind of trinary logic. The logic you were probably taught in school is a form of binary logic linked to Boolean algebra. It goes without saying that it has lots of uses, or else it would have fallen to the wayside and been forgotten ages ago. However, to probe statistical logic, we need to start with a kind of trinary logic. This form of trinary logic will be used to examine individual cases, where statistical logic will be used to build upon it to examine entire sets of such cases. Now, there are no doubt multiple systems of trinary logic out there, but the one needed for the study of statistical logic is the one that has the following three values: true, false, and non-applicable. I do not think that I need to explain what true and false mean. Those values are already there in the binary system of logic that you are familiar with. Non-applicable, on the other hand, means that the statement in question cannot rightly be ruled as true or as false in this particular instance. Let us take the following truth table that covers all situations in which each of the two input values is either true or false. Those input values let's call A and B. The AND operator in these situations works just the same in this system of trinary logic as it does in traditional binary logic. Likewise, the OR operator also works the same in all situations where the input values are either true or false. However, where the implication operator, also known as the if-then operator, is concerned, the behavior is different in this trinary system than it is in binary logic. If A is true and B is true, then A implies B is true whether we are in binary or trinary logic. Likewise, if A is true and B is false, then the output value will be false in both systems. However, things diverge when A is false. The rules of Boolean algebra, which is the mathematics of traditional binary logic, state that whenever A is false, then A implies B is true. However, in this trinary system, when A is false, then the value of A implies B is neither true nor false, but non-applicable. If you are familiar with the Trinary system of logic associated with Buddhism, you might be familiar with the value of none applicable, as there it is referred to as neither true nor false. You might be scratching your head wondering why I am not including an equivalent of the fourth option available in Buddhist logic, which is both true and false. The reason for this is that from what I gather, that option tends to be a reference to ambiguity in the statement being evaluated and is better dealt with by resolving the ambiguity than by adding a possible value. For example, where I read about Buddhist logic, the example given of a statement that is both true and false is "the egg is yellow." I suppose that this is in reference to your typical chicken egg. The statement is only both true and false in that it is an ambiguous statement that can mean a number of different things, some of which are true and others of which are false. For example, if by "the egg is yellow" you mean the visible surface of the egg is yellow, then the statement is false. It is not true at all, only false. On the other hand, if that statement means "the egg has yellow in it," then that statement is true because the egg does in fact contain a yolk, which is yellow. The statement is not at all false, only true. Or maybe it means the egg is entirely yellow, which is again only false. Or maybe the yolk of the egg is yellow, which is once again only true. Heck, it might even mean the egg's sports jacket is yellow, which is non-applicable or neither true nor false, as the egg probably does not have a sports jacket. In this trinary system of logic, no equivalent of the Buddhist both true and false value is included, because once the ambiguity in the statement is resolved, the possibility of a both true and false value tends to disappear. Anyway, that pretty much wraps it up for the introduction to this trinary logic system. Instead of just the values of true and false, you have the option of something being non-applicable, and as a result, the implication operator behaves somewhat differently. In the next part, I will discuss how this trinary logic examination of individual cases can be the basis of a cumulative examination of a whole set of cases in what I am presently referring to as statistical logic. When that part is ready, I will add a link to it in this video's YouTube description area. So until next time, see ya!